Now let's discuss about the Unit 5, which is the magnetism. So what is magnetism? Magnetism is a substance that possesses magnetic properties. It attracts iron and faces the same direction when moving freely. All materials have the property of being attracted or repelled. Let us know the history of magnetism. Magnetism, the natural force that causes magnets to function as they do, became known to people many centuries ago. They knew that the black metallic ore are called lodestone. It has the property of drawing particles of iron to it. The Greek philosopher named Thales, who lived during the 6th century BC, is said to have been the first to observe this property. After his time, the lodestone was often mentioned in ancient writings. It was given the name magnet after Magnesia, a district in the Asia Minor where large magnetic deposits are found. Now, let us know the classification of magnetic and non-magnetic materials. For magnetic materials, it has first the ferromagnetic. It became strongly magnetized in the same direction as the magnetizing field, with high values of permeability. Second is paramagnetic. It became weakly magnetized in the same direction as the magnetizing field. The permeability is slightly more than 1. And lastly is the diamagnetic. It became weakly magnetized in the opposite direction from the magnetized field. The permeability is less than 1. And for the non-magnetic materials, it includes air, paper, wood, and plastics. All magnets have two poles. Each of the magnet is called magnetic pole. Magnetic poles are always in pairs, one north and one south. In the properties of magnet, all magnets have two poles. Magnets exert forces on each other. Magnets are surrounded by a magnetic field. There are types of magnet. First is the electromagnet. That was made up of coils of wire and must have an external source of current to maintain a magnetic field. Next is permanent magnet. It retains its magnetic field indefinitely. How to make permanent magnets? There are 5 elements that can be made into magnets: iron, cobalt, nickel, aluminum, gadolinium, and dysprosium. But none of these elements can be magnetized permanently. To make a permanent magnet, you need an alloy. An alloy is a mixture of 2 or more materials. The best material for permanent magnet is magnequench, which was invented in 1985. This materials is mostly iron with a little neodymium and boron added. Let us know what is magnetic field. A magnetic field is a region around a magnetic material or a moving electric charge within which the force of magnetism acts. Magnetic fields are often represented by field lines that indicate both the direction and strength of the field. The lines are closer together where the field is stronger and farther apart where it is weaker. The strength of a magnetic field is measured in teslas, or Gauss, with 1 Tesla is equals to 10 Gauss. The Earth itself has a magnetic field, which protects the planet from solar winds and cosmic radiation. This geomagnetic field is essential for life on Earth. This picture explains how magnetic fields work. The left side shows that opposite ends of magnets, the north and south, attract each other. This means a north pole will pull a south pole closer. For the middle part shows a bar magnet with its north and south poles. It illustrates the magnetic field lines that spread out from the magnet. For the right side, shows that similar poles, north and north or south and south, repel each other. This means two north poles push away from each other. Each section mentions the direction of electric current in a wire, which is related to how magnetic fields can be created by electricity. So, it shows how magnets interact and how electric currents can create magnetic fields. Now, let us know about electromagnetism. Electromagnetism is the branch of physics that studies the interplay between electric currents and magnetic fields. The fundamental principles are: first, the Faraday's law of induction. It states that a changing magnetic field can induce an electromotive force or the EMF in a conductor. This principle is the foundation of many electrical devices. Second is the Ampere's law describes how electric currents produce magnetic fields. Electromagnetism is the basis for various technologies, including electric motors, generators, transformers, and wireless communication. Here in electromagnetism, Maxwell's equations belong. So these are Maxwell's equations. First is the Gauss law for electricity. Electric fields originate from charges. Second is the Gauss law for magnetism. The magnetic monopoles exist, magnetic field lines are continuous. The third is the Faraday's law of induction. Changing magnetic fields induce electric fields. And lastly is the Ampere-Maxwell law. Electric currents and changing electric fields generate magnetic fields. In magnetic field of a current, the magnetic field forms concentric circles around the wire. With the direction determined by the right-hand rule, if you grip the wire with your right hand, your thumb pointing in the direction of the current, your fingers curl in the direction of the magnetic field lines. The strength of the magnetic field B around a straight current carrying wire is directly proportional to the current or I and inversely proportional to the distance r from the wire. The magnetic field strength B is equal to the permeability mu multiplied by the electric current I divided by 2 times pi. So here is an example problem. Calculate the magnetic field strength 0.1 meters away from a long straight wire carrying a current of 5 ampere. To find the magnetic field strength B at a point of 0.1 meters away from a long straight wire carrying a current of 5 amperes, we use the formula of B is equals to mu 1 over 2 pi r. In this formula, mu represents the permeability of free space, I is the current flowing through the wire, and r is the distance from the wire. For this problem, mu is constant, which is the 4 pi times 10 raised to the power of 7 Tm per ampere. I is 5A and R is 0.1 meter. By substituting these values into the formula, we get B is equals to 4 pi times 10 raised to the power of 7 times 5 over 2 pi times 0.1. Then pi terms cancel each other out, simplifying our equation to B is equals to 4 times 10 raised to the power of 7 times 5 over 0.2. Calculating the numerator gives us 20 times 10 raised to the power of 7, while the denominator is 0.2. When we divide these values, we find that B is equals to 100 times 10 raised to the power of 7, which can be written as 1 times 10 raised to the power of 5t. Therefore, the magnetic field strength at a distance of 0.1 meters from the wire is 1 times 10 raised to the power of 5t, or Tesla.
So here is an example. Find the magnetic field 0.2 meter away from a long straight wire carrying a current of 8A. As we substitute these values, we get the answer B is equals to 4 microtesla. So for this example, determine the magnetic field at a distance of 0.05 meter from a wire carrying a 12A. As we substitute these values, we get the answer 24 microtesla.
Now let's proceed to geographic magnetic poles. It refers to the locations on the Earth's surface where the planet's magnetic field lines are converged vertically. These poles are distinct from the geographic poles and represent the points where the magnetic field is directed straight downwards into the Earth. Magnetic north versus geographic north. The magnetic north pole is where the Earth's magnetic field points vertically downwards. It is not fixed and moves over time due to changes in the Earth's magnetic field. The geographic north pole is the point at the top of the Earth's axis where latitude is 90 degrees N. So for the movement, the magnetic poles shift over time due to changes in the Earth's molten outer core, which generates the magnetic field. This movement can be several kilometers per year. And for the magnetic declination, because the magnetic north pole does not align perfectly with the geographic north pole, navigators must account for magnetic declination when using compasses. This angle varies depending on the location on Earth. For the geographic magnetic south pole, similarly, there is a magnetic south pole, which is the point where magnetic field lines enter the Earth. So for the force on a moving charge, the charged particle moving through a magnetic field experiences a force or a Lorentz force that is perpendicular to its velocity and the magnetic field direction. This force can be calculated using the formula F is equals to Q times V times B, where F is the force, Q is the charge, V is the velocity of the charge, and B is the magnetic field. So here an example problem. A charged particle with a charge of 2.0 times 10 raised to the power of 6 is moving with a velocity of 5 meters per second in a magnetic field of 0.1 Tesla. The angle between the velocity of the particle and the magnetic field is 90 degrees. So calculate the magnetic force acting on the charged particle. The magnetic force on a moving charge is given by F is equals to Q V times B sin. In this case, since the angle 90 degrees, we know that sin 90 is equals to 1. Substitute the known values in the formula and resulted to us F is equals to 1.0 times 10 raised to the power of negative 6.
In this example, where a proton Q is equals to 1.6 times 10 raised to the power of negative 19c, moves at 3 times 10 raised to the power of 6 meter per second perpendicular to a 0.2 Tesla magnetic field. Find the force acting on the proton. As we find the force acting on the proton, by substituting all these values, we get the answer F is equals to 9.6 times 10 raised to the power of negative 14 N. In this example, an electron Q is equals to negative 1.6 times 10 raised to the power of negative 19 C moves at 4 times 10 raised to the power of 5 meter per seconds in a 0.3 Tesla field at 45 degrees. So find the force on the electron. So by finding the force on the electron, by substituting these values, we get the answer F is equals to 1.36 times 10 raised to the power of negative 14N.
So for the force between two current, it is when two parallel conductors carry electric currents. They exert forces on each other. If the currents flow in the same direction, they attract. If in opposite direction, they repel. This interaction is a fundamental principle in the electromagnetism. So see the given formula stated. So here is an example problem. Consider two parallel wires, each 1 meter long, carrying a current of 5A and 10A, separated by a distance of 0.5 meter. Calculate the force per unit length, and by substituting these values, the result we get for the force per unit length between two wires is 2 times 10 raised to the power of negative 6 Newton per meter.
Two parallel wire carrying currents of 5A and 10A separated by a 0.4 meter. Find the force per unit length between them. So as we find the force per unit length between them, by substituting these values to the formula, we get the force per length is equals to 2.5 times 10 raised to the power of negative 6 Newton per meter. Two wires 0.3 meter apart can 6A and 8A in opposite directions. Calculate the force per unit length. As we calculate the force per unit length by substituting these values to the formula, we get the force per length equals to 3.2 times 10 raised to the power of negative 6 Newton per meter.
Now let us discuss the Unit 6, the electromagnetic induction. So, what is electromagnetic induction? Electromagnetic induction refers to the generation of electric current in a conductor which is exposed to a changing magnetic field. This phenomenon is critical to many electrical technologies. It was discovered by Michael Faraday in the 19th century. The principle of electromagnetic induction laid the groundwork for modern electrical engineering. Faraday's experiments demonstrated that moving a magnet near a coil of wire generates an electric current. Now let us proceed to key concepts. First is the magnetic flux. The total magnetic field passing through a given area, defined mathematically as the product of the magnetic field strength and the area perpendicular to the field. And second is induced EMF, the electromotive force generated due to the change in magnetic flux. So here is an example problem. This problem involving a coil with 200 turns placed in a magnetic field that changes from 0.5 Tesla to 1.5 T over a duration of 2 seconds. The task is to calculate the induced electromotive force generated in the coil due to this change in the magnetic field. Magnetic flux, which represents the amount of magnetic field passing through the coil, is calculated using the formula where B is the magnetic field strength, A is the area of the coil, and the magnetic flux is the angle between the magnetic field and the coil surface. The change in magnetic flux is determined by subtracting the initial magnetic flux from the final magnetic flux as the field strength increases. Faraday's law of electromagnetic induction states that a change in magnetic flux induces an EMF, which can be calculated using this formula, where N is the number of turns and the change in time is the time interval, and that is represent the change in magnetic flux. By plugging in the values and assuming the area of the coil remains constant, the induced EMF can be derived. This principle underlies the operation of electric generators and transformers. illustrating how a coil generates electrical energy when subjected to a changing magnetic field.
Find the magnetic flux for 0.1 meter squared loop in a 0.5 Tesla field at 60 degrees. As we find the magnetic flux, we get an answer 0.025 WB. A 0.3 meter squared coil is placed in a 0.4 Tesla field at 90 degree. Now find the flux. As we find the flux by substituting the values to the formula, we get the magnetic flux 0 WB.
So in Faraday's law, it quantifies how a change in a magnetic flux induces an electromotive force. So that is how the formula expressed as. It indicates that the electromotive force, or the EMF, induced in a circuit is equal to the negative rate of change of magnetic flux over time, with the negative sign reflecting Lenz's law, which states that the induced EMF opposes the change in the magnetic flux. So this problem involves a circular loop with a radius of 0.1 meters placed in a magnetic field that changes from 0.2 Tesla to 0.8 Tesla in 5 seconds. To solve it, we first calculate the area of the loop using the formula A is equals to pi r squared, which gives us an area of approximately 0.0314 meters squared. Next, we determine the change in magnetic field, calculate as 0.8t minus 0.2t, resulting in 0.6t. Applying Faraday's law of electromagnetic induction, we find the induced electromotive force, EMF, using the formula, and by substituting the values, we determine that the induced EMF is approximately negative 0.003768 volts. The negative sign indicates the direction of the EMF, which opposes the change in the magnetic flux as described by Lenz's law.
A loop with an area of 0.2 meters squared is in a field that changes from 0.6 Tesla to 0.2 Tesla in 4 seconds. So find the induced EMF. So as we find the induced EMF, by substituting all the values to the formula, we get the induced EMF equals to 0.02 volts. A coil with 300 turns is exposed to a field changing from 0.3 to 0.9 in 5 seconds. Area is 0.05 meters squared. Find EMF. So as we find the EMF, and by substituting all the values to the formula, we get the EMF equals to 1.8 volts.
Now let's proceed to generator. A generator is a device that converts mechanical energy into electrical energy using an electromagnetic induction. Generators operate based on Faraday's law of electromagnetic induction, which states that a changing magnetic field within a closed loop induces an electric force in the wire. There are two types of generator. The AC generator, were typically used in power plants and for household electricity. And the second is the DC generators, used in applications that require a stable voltage such as battery charging. Now, we have in transformer. A transformer is an electrical device used to transfer electrical energy between two or more circuits through electromagnetic induction. It is primarily used to increase or decrease voltage levels in alternating current system. So there are components of transformers. First is the core, second the primary winding, and third is the secondary winding. So there are also types of transformers. First is the setup transformer, second the step-down transformer, And third is the isolation transformer. And lastly is the auto transformer. So we are now in inductance, a fundamental property of electrical circuits that describes the ability of a conductor to store energy in a magnetic field when an electric current flows through it. The inductance of an inductor is given with this formula stated. Given this example problem, an inductor has 100 turns wire. When a current of 2A flows through the inductor, the magnetic flux linked with each turns is 0.005 Wb. Calculate the inductance of the inductor. Substituting the values to the formula we get, the answer is L is equals to 0.25 H.
An inductor has 150 turns and a 4A current produces a flux of 0.02 Wb per turn. So find the inductance of the inductor. So as we substitute all the values and calculate, we get the inductance of the inductor 0.075 H. An inductor has 200 turns of wire. When a current of 4A flows through it, then magnetic flux linked with each turn is 0.003 Wb. Calculate the inductance of the inductor. So as we calculate the inductance of the inductor, we get the answer 0.15 H.
Magnetic energy. It refers to the potential energy stored in the magnetic field due to the arrangement and movement of the magnetic poles or electric currents. The magnetic energy stored in an inductor is expressed as stated. Here is an example problem. An inductor in a circuit has an inductance of 5 henries. If a current of 2.5A flows through the inductor, calculate the magnetic energy stored in the inductor. By substituting this value to the formula, we get an answer of 15.625 joules.
A 10H inductor is carrying a current of 5A. Calculate the energy stored in the magnetic field of the inductor. So as we calculate the magnetic field of the inductor, we get the answer 125 joules. An inductor with an inductance of 4H carries a current of 3A. Calculate the magnetic energy stored in the inductor. So as we calculate the energy stored in the inductor, by substituting all the values, we get the answer 18 joules.
Now let us know what is electrical oscillation. Electrical oscillation refers to the repetitive variation of electric current or voltage in a circuit over time. It is a fundamental concept in electrical engineering and physics, particularly in the study of alternating current system, resonant circuits, and signal processing. There are types of electrical oscillation. First is the free oscillation, second is the damp oscillation, and the third is the driven oscillation. So that was all the topic of Unit 5 and Unit 6. I hope you understand and learn from it.